Alright, welcome back again. In this video, we will be looking at isomerism, but this time we are going into more details and looking at different isomers. So the isomers you would have been accustomed to would be the structural isomers. So for isomers, we have two main categories. We have the stereo isomers and we have the constitutional isomers, which is also referred to as structural isomers. So we have stereo isomers and structural. Now stereo isomers are further branched into optical and geometric. Geometric is also referred to as cis-trans and will only occur in alkenes. So you can just remember that from now. Geometric isomers occurs in alkenes. And we have optical isomers, we also call them enantiomers. For structural isomers, you can have the chain, positional, functional group. Right? So the two categories, structural and stereoisomerism. Under stereoisomers, it's optical and geometric. For structural, you can have chain, positional, and functional group. So first, we're going to look at the structural isomers. So we all know that isomers are compounds with the same molecular formula, right? But their arrangement is different. So we are looking at structural isomerism. Alright, so for structural isomerism, we know that the compounds must have the same molecular formula. Alright, so they must have the same molecular formula but different structural formula. So the first one we're going to look at is the chain isomer. Alright, so for the chain isomer, so all of these isomers, we know that they must have the same molecular formula. But with the chain one now, the arrangement of the carbon atoms are different. So remember, structural isomerism is referring to chain, position, and functional group. The chain one, the carbon atoms, they must be arranged differently, and this is the one you are familiar with. So for example, C5 H12. Right? So we know that 5 carbons, it's an alkane, so it has to be pentane. Now if you want the next isomer and you have to change the arrangement of the carbon atoms, it means we have to remove a carbon from the chain, right? So we have pentane. If you remove a carbon, that means our new chain will have 1, 2, 3, 4 carbons. So that would be butane. And again, you should know that we don't put this carbon that we take off, do not put it back at the end. If you put it at the end, the shape will look different, but it's not, it's the same compound. 1, 2, 3, 4, 5, that is pentane. So when you take it off, do not put it back at the end. Put it on one of the carbons within the chain, right? It's somewhere in the middle. So if you put it on this carbon, when you put it below or above, it's attached to the same carbon, so it doesn't matter. So here we have a methyl group and carbon 2. So we have 4 carbons, so we know that that is butane. We have a methyl group, so it is methyl butane, and it's on carbon 2, so it is 2-methyl butane. So clearly, the arrangement of the carbon atoms in these two compounds are different. And we can get a third one. So again, we're going to remove a next carbon from the end, right? You should know that if you shift this carbon to this one, it would still be 2-methyl butane, because if you move it from here and put it here, it would be closer to this end, so you would count from here, which would make it 1, 2, right? So shifting it from here to here will not work because it will be the same compound. So if you take off a next carbon, remember, you cannot put it back at the end. So the only place it can go is the middle one. I have done videos on the channel for this already, for this type of isomer in detail, so I'm not going into details again on how to get them. So we have 2 CH3 groups now. So the chain 1, 2, 3 carbons, so we know that that is propane. We have 2 methyl groups, so we know it is dimethyl. And they are on carbon 2, so it's 2, 2 dimethyl propane. So if you want to chain isomers, you must change the arrangement of the carbon atoms in the compound. And of course, the molecular formula must be the same. So if you check, 5 carbons, 3, 3, 3, 3, 4 trees, 12 hydrogens. 5 carbons, 3, 5, 7, 9, 12 hydrogens. Again, 4, 5 carbons, 3, 6, 9, and 3, 12 hydrogens. So all of them have the same molecular formula, but the arrangement of the carbon atoms is different. Alright, so we're going to move on now from the chain isomers to the position ones. So we're going to move on now to positional isomers. Now, with the positional, we won't be changing the arrangement of the carbon atoms. We are going to be changing the position of the functional group or a particular substituent group. So in positional isomerism, we can take out this part. So in positional isomerism, the functional group or substituent group is in a different position in each compound. Alright, so for example, let's use C3H8O. Once you see a compound with carbon, hydrogen, and 1 oxygen, it can be an alcohol. So let's check the molecular formula and see if this structural formula can work. So now we have the 3 carbons, we need 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. 1 oxygen. So here we have 1 propanol. So we're going to change the position of this functional group. So now the OH is on this second carbon. So it's 2 propanol. Or if you want to say propan, 1 al, and propan, 2 al. Alright? So the arrangement of the carbon atom is the same. We're not touching the carbon atoms. We are shifting the position of the functional group That's it. Chain isomer is the one where we are going to change the arrangement of the carbon atoms. Alright? So next example, let's do it here. Alright? So for this compound, it's 1 chloropropane. Let's see if that can hold. Would be 1 chloropropane. Alright? And this would be 2 chloropropane. So we have 1 chloropropane and 2 chloropropane. So again, we are moving the position of the substituent group here, the Cl. So again, same amount of carbons, same arrangement, but the position of this substituent group here, it is different. So that is how you would get the position isomer. Alright, so that's positional isomers. So the next one we're going to do now is the functional group. So with functional group, the two compounds again having the same molecular formula, but this time they must have a different functional group. So again, sticking to the rule, the compounds must have the same molecular formula. So for example, C4H10O. So same molecular formula, but they must have a different functional group present. So if you see the compound with 1 oxygen, right, that's possibly an alcohol. So let's draw an alcohol and see if it matches with the functional group. Alright. So 4 carbons, 3 and 2, 5 and 2, 7, 10. So C4H10O. So this is 2-butanol. When you have one oxygen, the next possible functional group is an ether. I want to say ether, E-T-H-E-R. So carbon, single bond, oxygen, single bond, carbon, that's an ether. Alright? So let's complete it and see if it matches the functional, the molecular formula. Now you don't have to put the two carbons, like two carbons on each side. Just draw the oxygen, carbon, carbon. That's the ether. Then, if you wish, you could have put 3 carbons on this side and 1 carbon on this side. It doesn't matter. Just ensure you have this functional group. So this we have an ethyl group on this side, CH2, CH3, that's the ethyl group. So we have 2 ethyl groups, so we can just call it diethyl ether. Alright? Or we could say ethoxy ethane. So you could say diethyl ether or ethoxy ethane. Once you hear ethoxy, you know it's an ether. This portion of the ether, as you notice, the prefix ETH, that's 2 carbons. So ethoxy ethane. One part has 2 carbons, the next part also has 2 carbons. Ethane, 2 carbons. So this part, the longer carbons, the longer chain, that would form the alkane. So 1 carbon here, that would be methoxy. So use the red. Methoxy. It's 3 carbons, so it is propane. So methoxy tells you that you have 1 carbon, a CH3 group, propane, you have a propyl group. So another name you could have said, if you wanted to do it in this form, it would be methyl propyl ether, right? Or methoxy propane. So whichever way, alright? So methoxy, once you hear methoxy, that means it's an ether. Propane, so the oxygen separate the 2 carbon chains. Methoxy, that's a CH3 group. Propane, that's CH2, CH2, CH3. 3 carbons, 1 carbons. If you hear ethoxy ethane, then you have 2 carbon chains on each side of the oxygen. So all you are doing is naming both sides of the oxygen differently. But if they are the same, as in this case, it's diethyl because it's 2 ethyl group. Or in this case, 2 carbons ethoxy, the other 2 carbons, that's ethane. So that's it. In this one, it's methoxy, 3 carbons over here, propane. So back to the important point, functional group isomers. You get the same molecular formula, but the 2 compounds you draw must have a different functional group. So if you draw 2 butanol, you are not going to draw these 2, you know, just 1. I just did this as a second example for the ether. So these two would not be functional group isomerism. Obviously, they have the same functional group. But any one of these with 2-butanol is functional group isomerism because you have the same molecular formula. Check it. 3 and 2, 5 and 2, 7 and 3, 10. That's 10 hydrogen, 4 carbons and 1 oxygen. So the same molecular formula, but the two compounds have a different functional group present. So that is functional group isomerism. So if you get one with 1 oxygen, so it's carbon, hydrogen, 1 oxygen, most likely it's a butanol and most likely it's your alcohol and the ether. Alright? If you get one now with 2 oxygen, let's do one with 2 oxygen. So, if you notice, we have, once you see this, you should know that this is the ester functional group, and right here is the carboxyl functional group. So let's check if the molecular formula is the same. 1, 2, 3 carbons, 1, 2, 3 carbons. So that is C3. 3 and 2, 5 and 1, 6 hydrogens. 3 and 3, 6 hydrogen again. And both of them have 2 oxygen. So again, you can see that it's a functional group isomer. This one have an ester, this one is a carboxylic acid. So it is propanoic acid. And this one is methyl ethanoate. That's the ester. Alright? So same molecular formula, but the two compounds have a different functional group. So everything, same molecular formula, but something about the compound is different. So with chain isomer, same molecular formula, but the arrangement of the carbon atom is different. With positional isomers, they have the same molecular formula, but the position of the functional group or substituent group is different. And for functional group isomers, same molecular formula, but the compounds have a different functional group present. So that's it for constitutional or structural isomers. So the three of them we must know: positional, functional, and chain isomers. So we're going to move on now to the stereo isomers. I'm going to end this one here and do stereoisomers as a separate video. Alright, so that's it for constitutional isomers. I'm going to pick up stereoisomerism in a different video. So remember to like, share, subscribe, and click the notification bell so once I upload, you will be notified.